Welcome to Lecture 27, Chapter 7. Alright, so 7.1, Properties of the Normal Distribution. So for the first objective, we're going to use the uniform probability distribution. So let's take a look at the first example. Suppose you had 15 $100 bills and you decided to stand on the street corner and hand $100 to someone who walked past you. Anyone who happened to pass by you would have an equally likely chance of getting a $100 bill. So the graph of a uniform distribution is usually flat, whereby the sides and top are parallel to the x and y axis. So if we had our x and y axis, we could go ahead and we could graph our normal distribution, or uniform, distribution. Now, the percentage of the probability for a person getting a $100 bill would be 1 divided by the total of number of outcomes, right? So 1 divided by 15. Where the random variable, capital X, is the person who gets one of the $1,500. So the random variable can be any value in the interval of 0 to 15. All right, so graphing our uniform probability distribution, we have the density, or the probability, which in our case would be a 15th for anybody who happened to go by, right? And all of these values go up to from 0 to 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We go ahead and extend our graph a little bit. So there we go. And that would be the density function, which is pretty much shaped like a rectangle. So it's easy to find the area of these. But one thing to remember to note for our functions, the area underneath them is going to be 1. And sorry about the low audio quality on my video right now. My microphone is not working well, so I'm doing what I can for the videos. Hopefully you can hear me well enough. All right, so for the definition. What is the definition? Well, a probability density function or PDF, not the kind you turn in, is an equation used to compute probabilities of continuous random variables. It must satisfy the two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1, and the height of the graph of the equation must be greater than or equal to 0 for all of the possible values of the random variable. So note, these two properties are very similar to the properties that we had for a discrete probability distribution. And also note that the area under the graph of a density function over an interval represents the probability of observing a value of the random variable in that interval. So for example 2, area as a probability. Now we're looking back at example 1. So what is the probability that the 5th, 6th, 7th to 8th person to walk by has got a $100 bill? Sorry, that's a little incorrect for the grammar there. I'll be changing that on your notes. So what's the probability that the 5th, 6th, 7th, or 8th person got a $100 bill? Well, let's go ahead and take a look at the probability that we had. Remember, it was 1 out of 15. So let's go ahead and we're going to copy down the graph that we had previously. So remember, we had density, and then we had the person. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we're looking for people from 5 to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we are looking at the density of the area right here. What is this probability? 5 to 8. Well, how do we find that probability? We're going to go ahead and just multiply the normal probability for this area, which is 1/15th, by each of those independent miniature intervals. So how many of them are there? Well, from 5 to 8, there are 3. So what we're going to do is we take 3 and we times it by the probabilities, which is 1 over 15. And remember, we got 3 because there are 3 sections. Sorry, my graph is not perfect. That's the 3rd section. All right, so let's see. 3 times a 15th is going to be 1/5. So that is our probability. So the probability is a 5th. All right, so there is a 20% probability that you will give $100 to which person? All right, let's go ahead and take another look at what this density function would look like. So let's go ahead and graph it again. We have our 15, and we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's bring that down. Let me erase the excess. And we are trying to figure out, now this time we're given the area. Okay, so we're looking for a 20% area. So I don't actually know which number this one corresponds to. Let me change that color. I don't know what number person this corresponds to, but I do know that the area we're looking at is 20%. So this time we're given the area and we want the percent. So we're going to use the same sort of formula we had last time, which was we had our person, which is the x value, remember, x times our probability, and this time we're actually given the n%, which is 20% or 0.20. Okay, so solving, we're going to solve or multiply both sides by 15, and we'll get x equals 15. Oops, that was ugly. 15 times 0.20, so x equals 3. So given to, or it will be given to, the 3rd person. Or a 20% probability it'll be given to the 3rd person. So, graphing a normal curve. We can use a rectangle to find the probability of observing an interval of numbers for a uniform random variable. However, not all continuous random variables follow a uniform, ran out of space there, a uniform distribution. Uniform distribution. Because of this, we use the curve to model the probability distribution of a continuous random variable. All right, so in math, a model is either an equation, table, or graph that we use to describe the real world. All right, and hopefully when we've described the real world, we can then actually solve problems off of things that we have created and the models that we've created. So definition, a continuous random variable is normally distributed. Or has a normal probability distribution, if in its relative frequency histogram has the shape of a normal curve. All right. Also, for symmetric distributions that have a single peak, what do I mean? Well, when we're talking about a single peak like this versus something that might look something like that, so we're now looking at the single peak variety. What do we know? Well, the median, mean, and mode are going to be equal. And also, the points at x equals our mean minus 1 standard deviation, and x equals our mean plus 1 standard deviation, so this is in the 68%. Remember, if we're using the empirical rule. What are these called? These are called the inflection points on the normal curve. And this is where the curve or the slope of the graph changes. So let's take a look at an example of what I'm talking about. All right, so, wrong pen. Let's say we have our graph line, and then we have our normal curve. Let me draw that end a little bit better. Okay, so we would have our mean, median, and mode right in the middle, struggling here to draw. Okay, mean, median, and mode. And then we have the other things, the important parts called the inflection points. So that is where our curve changes. So if you take a look at this, where would you think the 2 points change on our curve? Well, between here and about here, it looks like our curve is pointing, it's doing this upward shape, right? But then, as I start to get to this section here, my curve actually looks like it's downward. So it's doing this sort of a shape. So it's doing a downward portion at this end, and then about here on either side is where it switches and it flips and it starts to become an upward facing curve. Okay, so here we have the downward, basically around from here to here. And then from the other portions, we had sort of an upward facing curve. So where that happens, at this point here and here, those are the inflection points, which would be x equal to 1 standard deviation away from the mean on either end. All right, so now for objective 3, we're going to state the properties of the normal curve. So what do we know? Well, we know that the probability density function satisfies all of the requirements of probability distributions. So now let's take a look at the properties of the normal density curve. All right. 1, the normal curve is symmetric about the mean mu, which is really nice. What do we mean by symmetric? Well, it is perfectly equidistant on either side, going around like this. It is not something like, let's say, if it's skewed, if we had our mean here, the distance from this point to the middle is different from the distance from this point to the middle. So we're looking at these, not those. All right, the next thing. Because we know that the mean, median, and mode are all equal, so the mean, median, and mode are equal, the normal curve has a single peak. And the highest point occurs at our mean. Next, we know that the normal curve has inflection points at mu minus sigma and mu plus sigma, which we went over. And the area under the curve is 1. Next, the area under the normal curve to the right of mu, let's get a visual here. So if we have our normal curve, and here's mu, the area to the right, we're talking about red. So the area to the right of mu, oops, let me take that back. So the area to the right of mu, sorry, wrong word is supposed to go there, equals the area under the curve to the left of mu. Okay, so now let me color code these. So this is the area to the left, left of mu, right of mu. And each of these areas, this side and this side, because they're supposed to total up to 1, remember, they're each a half. Because the total area is 1. Next thing to note. As x increases without bound, which also means it gets larger and larger, the graph approaches but never touches the horizontal axis. What does this mean? Well, let's go ahead and take a look again at the normal curve. So where would x be getting bigger and bigger? Well, on the normal number line, which is what I'm going to highlight in yellow here, if I start going off into this direction, my x values are getting bigger and bigger, right? If I was to head off in this direction, my x values would be getting smaller and smaller, or decreasing. So here we're talking about as x increases. So as x increases, what is happening with my graph? Well, as I go along, my graph starts to slope downward towards the horizontal axis, but it's never going to actually touch it. Next, we look at a very similar option as x decreases without bound, and this gets smaller and smaller. The graph approaches but never reaches, once again, a horizontal axis, which you can see here as it heads off in that direction. Now for the empirical rule. Awesome thing is we can use the empirical rule with this. Yay! So approximately 68% of the area under the normal curve is between mu plus 1 standard deviation and mu minus 1 standard deviation. Hopefully by this time you have these memorized because these are going to be used often. Next, we have that approximately 95% of the area under the normal curve is between mu plus, and here we go, 2 standard deviations and mu minus 2 standard deviations. Then, lastly, 99.7% of the area under the normal curve is between mu plus 3 standard deviations away, and lastly, mu minus 3 standard deviations away. And that's talking about from the middle. So we have, if this was 1 standard deviation away, this would be our area for 68%. Then this would be our area for 95%. And lastly, the area for the 99.7%. Now let's take a look at a small quick example for how histogram can fit the normal curve. If you want a more in-depth example for this one, you can go ahead and read in your textbook. I believe it is on page 333 if you want a more in-depth example for this. But so basically, if you have a histogram, we can go ahead and approximate it to fit the normal curve like so. And if you get enough of these rectangles in each area, it comes out to be approximately equal to these areas added together. Because notice these are all rectangles, so if we add all these areas up, the approximation would be similar to the area of a normal curve that we drew over the histogram. All right, that was a very simplified example of what that means. So the probability density function is given by what equation? Well, the equation is kind of an interesting looking one. So y equals 1 divided by sigma 2 pi times e to the negative x minus mu squared all over 2 sigma, squared. It looks hideous, but don't worry, we will not be using it in this class. But it's a good idea for you to at least see what it is. All right, so note we are not going to be using that in this class. All right, now let's take a look at area under a normal curve. Suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristics described by the interval of values or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. Now let's take a look at the last example, interpreting the area under a normal curve. All right, so the serum total cholesterol for males 20 to 29 years old is approximately normally distributed. So approximately normally distributed means it's not perfectly normally distributed, but close enough we can use the values or the applications. So with a mean mu equal to 180 and sigma or standard deviation equal to 36.2 based on data obtained from the National Health and Nutrition Examination Survey. So note, an individual with cholesterol greater than 200 is considered to have high cholesterol. Draw a normal curve with the parameters labeled. Shade the region under the normal curve to the right of x equal to 100. All right, so we have our normal curve. Our parameters are our mean, so 180. And then now we're going to be drawing in our inflection points, which are now part of the parameters. Okay, so note that inflection points important in your parameters. So always draw at least the 1 standard deviation away, which, calculating it out, is 143.8 and 216.2. How did I get that? Remember, 180 plus our standard deviation gives us that. And the reverse direction, 180 minus our standard deviation, gives us the 143.8. So what are we trying to find? We are trying to find the area, or shading in the area to the right of 200, which we're going to guesstimate here is about here. So we're trying to find this area here. Suppose that the area under the normal curve to the right of 200 is 0.2903. Okay, actually, sorry, we're given that area. We're not finding it yet. We'll actually find that area, or practice finding it, in 7.2. So we're given that this area is 0.2903. Provide two interpretations of this result. Okay, so we're going to base this interpretation off of these two, the two options. So what are the two options? Well, we could do the first one, which is talking about proportion. So the proportion, proportion of males 20 to 29 that have high cholesterol is 0.2903. Cholesterol is a hard word to write. And the second interpretation, let's take a look again at the top. It is the probability. Okay, so let's see. This is saying the probability that a randomly selected male 20 to 29 years has high cholesterol is 0.2903. So two interpretations, proportion and probability. So C, what is the proportion of males 20 to 29 years old that do not have high cholesterol? Use the fact that the total area under the curve is 1. Okay, so we're trying to figure out the proportion that doesn't have high cholesterol. So those are the people whose cholesterol is below or to the left of 200. And we know the total area of this whole thing is 1. So to find the area in yellow, what should we do? Well, we'll do 1 minus 0.2903. So 1 minus 0.2903, what do I get? Is 0.7097. And what does this result mean? Well, we could interpret it using either one of these options. Let's go with the proportion. So the proportion of males 20 to 29 years old that have that do not have high cholesterol, is 0.7097. You could also say the probability of selecting a male 20 to 29 years old that has high cholesterol, that does not have high cholesterol is 0.7097. So once again, two different ways to write your final answer. All right, that is it for this section. Please email me if you have any questions.